First, I'd like to ask a favor. I have a runny nose. Feel terrible. But anyway, the topic we'll be discussing today, excuse me, is the model known as structural vector autoregression. Maybe you heard of that from your macroeconomics class. One of our faculty members recently joined, Professor Nam. He has a specialty in this area, and he deals with much bigger model than this one, but I think you can understand the basic structure of that approach from this lecture material. So, because we have 2 more classes this week, and then exam next week, so I try to cover structural VAR today, and this Thursday, I try to introduce you generalized method of moments method, which is also very important time series technique. Okay, here is some motivation. When we discussed ordinary vector autoregression, we know that the innovation terms, the residual terms, are often difficult to interpret because it has any meaning. It's just a mechanical thing. And when we try to calculate impulse response function, we didn't intend it, but in somehow by applying Cholesky decomposition, we are building a system of equation in a recursive way. Okay. But in reality, things are not determined one by one. It's determined at the same time, right? But because of the structure of the original VR approach, you can't avoid that. So our motivation here is, well, in other instance, if you make some reasonable assumption, you might be able to identify residual or innovations which may be interpreted in more economic terms. Okay. So here is an example borrowed from Blanchard and Quah. Looks like he's a French, so Blanchard or Blanchard. In 1989, they looked at this problem where you can think of y of t as natural log of real GDP, okay? Some real variable. Okay? And we take the difference to make it, growth rate, which is stationary, right? What determines that? Well, this model, notation may be a little bit unfamiliar to you, but we'll get to the detail of this. But here, this thing, C11K, or C12K, or this, or that, those are numbers, a function of K. Okay. And then this epsilon, AD, is what we call aggregate demand shock. Let's call it aggregate demand shock. And another set of innovations, we call it aggregate supply shock. Okay. In a macro 101, typically you work with this demand and supply side of the economy in aggregate. Okay. And what we mean by AD shock is something that changed this one. By every supply shock, that affects the location of supply curve. Okay? You learned what determines this. For instance, what? Monetary policy shock, or money demand shock. People suddenly, move away from cash, sort of thing, right? So behavior change. Those fiscal policy, of course, fiscal policy and monetary policy and the shock associated with those two may affect the location, right? And supply shock could be, a sudden increase, surge in oil price, for instance, right? So those shocks will have effect on Y and some companion variable Z. Z could be any variable, depends upon the way you formulate this one. I believe Blanchard and Quah used unemployment rate here, detrended unemployment rate, which is stationary. Okay, but let's just take this one as just any ordinary variable expressed in terms of growth rate, which is stationary. Okay, so it would be nice. Well, actually, all you have is these two, right? The data, right? And the question is how to identify those shocks. So you might be interested in, what would be the effects of current aggregate demand shock on the future path of real GDP growth rate, okay? Or unemployment rate, so on. Let's take a look at more detail of this part. If we let Cij of L in this way, where we have two variables, so 1, 1, or 2, 2, or cross, right? As a polynomial, so you have L 0, L equals 1, 2, and so on. So we can use this compact notation to rewrite previous infinite sum, okay? As long as this goes to infinity. So same thing. Probably it is difficult for the moment to visualize how this looked like, but bear with me. It's something you can actually calculate. Obviously, if you know this number, scalar, everything, then you know this one, right? What are those? What are those? Well, actually, if you take a look at this one in particular, here, okay, let's say this is C1, 1, 1, 1, this is 1, 1, and what is this coefficient implying? Well, it's related to second leg, right? Second leg. So that this is impulse response from the shock occurring at t minus 2 on t, or shock occurring at t and t plus 2. Right? So these are measuring impulse response. Okay? We can rewrite the above equation in this compact notation. So, that has 4 elements, right? This one. And obviously, this epsilon t consists of aggregate demand shock and supply shock, right? So vector, 2 by 1 vector. So 2 by 2 matrix of polynomial in L, and this is 2 by 1. Right? To identify this from data, the first assumption, typical assumption made is these innovations are normalized and they are not contemporaneously correlated. By that, what we mean is obviously expected value of that is 0. So this expression amounts to the covariance matrix, which is 2 by 2. And this is normalized, so these are assumed to be 1. And no correlation, that means 0. Okay? So that's one identifying assumption. But there are other identifying assumptions. The one, assumption 1, you can think of this is the case. Well, aggregate demand shock has a temporary effect on real GDP, whereas aggregate supply shock has a permanent effect. So probably you recall from your Econ 101 that the shocks to this curve is permanent, often permanent, whereas the shock, monetary shock or fiscal shock, they are lasting only temporarily. Okay? So if that is your assumption, we can use this one to identify structural innovation epsilon. The assumption 2, we don't make any assumption about Z, so neither shock affects permanently on Z. Okay. What this tells you can be translated into this term. Well, let's see. Usually, if y follows autoregressive process, then we can, as long as it is stationary, we can divide this polynomial on both sides, right? So get this one. And if it is AR1, for instance, then this is basically infinite order moving average process, right? There will be shock. All those shocks, what is the effect of shocks on y? Well, when you calculate that, basically, by replacing this one by 1, we are adding actually all those coefficients. Right? That's the long run effect of epsilons on y. Okay? So that is very similar here. Since the long-run effect of AD shocks on real GDP is computed by replacing lag operator L by 1, so we're effectively adding those all coefficients, right? All those coefficients. In the long run, because we assume that AD shock affects real GDP in the short term, but in the long run, we assume that it dissipates. It doesn't last, right? So it goes to 0 if horizon increases to infinity. Okay? So this assumption is equivalent to this one. Okay? Still, we'll be using this condition later on. But let's, for the time being, let's keep going and see if whether we can identify this sequence. Well, because we have only data x, and if you run a VAR estimation, and typically what you get is this one. We didn't write VARP process in this way previously, but later you will see that what's the exact meaning of this one. But for the time being, let's think of this way: even if you have VARP, so you're looking at lag all the way up to p. As well, the thing, what is called a companion form, is to relate x and its lag using polynomial only. Okay, so you don't have any p lags here. Okay. So let's think of this one as a just usual VAR p representation. And A of L, because it has two dimension, this is two-dimensional vector. We have 2 by 2 matrix polynomial in L, and you have a residual. Okay, so running a VAR estimation is to fit this model and obtain coefficients associated with that, and as well as these innovations. Okay? So we start, our focus is to estimate this one, identify this one, but we start with something different, just the usual residual vector from general VAR model. Okay? And from fitted residual, we have covariance matrix, where you have variances and covariance, but they are the same, right? So Blanchard and Quah decomposition of the variation of x into something what we call permanent component and something called temporary component is to, it amounts to calculating C of L and sigma hat. Sigma hat, we already assume that this is identity matrix, so we don't estimate this one, right? We assume identity matrix for this one, but we still need that and this one using A hat of L, which is defined later, and covariance matrix, and fitted residual from VAR estimation. Okay. So we'll start with VAR estimation and get this, that, and then try to recover this one and that one. And let me show you how. Here, this is starting point. What is the relationship between structural residual epsilon and ordinary Booyer innovation E of t? The relation is here. The reason why they are the same this is innovation at t. So one step ahead forecast error, right? This one. That's innovation. And if you look at the innovation at t, that's same as k equals to 0, right? So C11 that, C12 that, right? Also C210, C220, and that. So 2 by 2. So those residuals should be the same. So we get this relation. So if you can get this one from ordinary VAR, as long as you know what that is, these 4 numbers, you can calculate this one as epsilon t equals to C0 inverse multiplied by ET. Right? Like that. So estimating this one is our objective, right? Our goal. Then how to calculate C of L? Our previous VAR representation is now rewritten in this form because we had xt and there was xt minus 1 with this. Okay? So you can operate this one in this way, right? This is 2 by 2, right? 2 by 2. So you can think of there is a identity matrix with dimension 2 is multiplied. And A of L times L xt, right? So bringing that term to the left-hand side and factor out. And assuming stationarity, we divide this thing on both sides to get this result. Okay. So this is the one we can formulate using Booyer representation, and also we know that xt is related to the structural innovations in this way. So these x's are the same. So this has to be the same as this one, right? So there, because this is, we know that this has to be C0 times epsilon t. So what has to be this one? Of course, that, right? This one. So if you can calculate C0 as 2 by 2 matrix, this one, and if you know all those A of L parameters, then you can calculate this one. Now let's turn to the problem of calculating C0. Okay? Because E of t equals to C0 epsilon t. So what is the variance of that? From VR estimation, our notation was omega, right? Omega. What is the variance of this one? Applying Kramer's rule, where if you have a vector and matrix multiplied, then these times covariance of that times C0 transpose. Right? But the covariance of epsilon t is assumed to be identity matrix. Right? So disappears. So this one. So see the dimension? This covariance matrix look like this. Right? How does this one look like? Well, this way. Okay. But these two are the same. There are 4 unknowns. 1, 1, 1, 2, 2, 1, 2, 2. Right? So how many equations here? 3 equations. But unknowns are 4. Right? So you can't solve it to find C0. Right? So you need one more assumption or equation. So that equation, another equation, is derived from previous identifying assumption in equation 2, and this is the way you do it. A little bit of algebra is involved. Let D is a determinant of this matrix polynomial. And then, we had previously this expression multiplied to there, right? And then we rewrite this one, because this is inverse matrix. When you follow matrix algebra, the inverse matrix of this one is this 2 by 2 matrix divided by determinant. So a little bit of matrix algebra is involved here, okay? Linear algebra. For the moment, let's take this one as correct. Okay. Actually, this is correct. Well, because you have 2 variables in this xt vector, right? So first component was delta yt. So we rewrite this expression in terms of first equation, delta yt. So if you carefully write that for delta yt, in this way. Okay. So here is our E sub first residual in ordinary VR, the second residual in ordinary VR. Okay. And we know this is simply that, and this is simply that. We can rewrite this equation as this one. Okay. Right. The first one is this one. The second one is this one. Okay. And then we factor out. Okay. So one involving AD shock, the other including AS shock. Okay. If this inverse matrix is well defined, then we know that determinant is not 0, right? Determinant is not 0. So what has to hold here is, because AD shock has no permanent effect on YT, this part has to be 0, this part, this one. So this part. So translating our identifying restriction A1 to this equation is the last puzzle of this problem. So this will serve as the fourth equation. So we had 3 equations, 4 unknowns. Now we have 4 equations and 4 unknowns. These are unknowns, and these will be computed from VR estimation, believe it or not, but you will see it shortly. Okay. So you are curious about what this means, right? What this means. So let's take a look at this example. You have pair of equation, leg 1 and leg 2. So this is VAR2, right? This is the usual way of writing VAR model, right? But our previous representation of VAR, ordinary VAR, was rewriting this equation in terms of this way. See? So this multiplied by that, right? So 0.5, this one is right here. Sorry, just a second. Right, this times that, and see, 0.5 times that is this one. 0.2 times 2 legs, right? 0.2 times 2 legs, right? Second one. And similarly, this one and that. Right? So when you write it this way, this is A of L. 2 by 2, function of L, right? So this part is A11L. This is A2 to L. A1 to L, A21L, right? This one. So by defining this part as a matrix polynomial in this way, you can write the relation between xt and xt minus 1, not having xt minus 2. Right? This is simply just rewriting this equation in terms of this. Right? So xt equals to A of L xt minus 1 plus et. So that was the previous setup. Okay? So if you estimate typical VAR, you have all these numbers, right? So you can fill it in, everything, right? And then plug in 1, 1, 1, 1 to get this number and that number. Okay? So you have this part known, known, and 2 unknowns. Okay? So here, A2 to 1, 2 to 1 is 0.3 plus 0.4 times 1, which is 0.7. So these are 4 equations. These are the estimate from VAR, unknowns, estimate, unknowns, and estimates, unknown. Right? So by solving this 4 equation, simultaneously, you get the answer. But as you know here, how do you solve these 4 equations for unknown problem? Well, in Gauss or in other software, they usually provide a nonlinear equation solver. So you set up number of equations, and then it will find solution. In this case, C210 is a parameter. It is squared, right? It is squared. So the relationship here is, this is nonlinear, right? Nonlinear. So basically what we can think of is the algorithm I show you shortly. You bring everything to the left-hand side. So subtracting this one from that has to be 0 if you solve this system at the same time, right? So bring everything to the left-hand side and let's make it 0. Do the same thing, right? And see if all those difference between these are 0. Okay. If our solution is correct, then equality should hold, right? So let's take a look at real example. What I brought is from my textbook, where we were interested in modeling real exchange rate and nominal exchange rate. This E of t is natural log of nominal $1 exchange rate. This is monthly, starting from 1980 to just before the outbreak of currency crisis in 1997. So we know what happened in November and December, right? Exchange rate exploded. This is bilateral real exchange rate. So the way we calculate it is you add CPI, of course, in terms of natural log, of country in the denominator, which is US. And this one is our Korean CPI in natural log. Okay? You probably guessed why I brought this nominal exchange rate and real exchange rate. Well, to apply this Blanchard and Quah decomposition, we have to think about 4th restriction, identifying assumption. Structural shock, if something, let's say, is defined as real shock, real shock will affect real variable in the long run, right? Nominal variable as well. But if it's nominal shock, it will affect real variable temporarily, but not permanently, right? So we try to use that. But let's take a look at more detail here. So this is VAR estimate. I take, because this real exchange rate and nominal exchange rate, the name of variable is log $1, and this is the real $1, okay? Or in natural log. So by calculating 100 times difference, first difference, that's the growth rate or rate of change expressed in terms of percent, right? In terms of percent. So first equation and second equation. And this is VAR2, right? VAR2. So we need those coefficients to define A of L, right? A of L. And constant appears to be insignificant, but leaving it there won't hurt. So this is the result, VAR2, and we can rewrite it in terms of companion form. And this is our structural VAR model in this setup. So this is the rate of change of real exchange rate, and this one is for nominal exchange rate. And the first shock, I assume this is a real shock, okay, real shock. The second one, nominal shock. Okay. So nominal shock can affect real variable temporarily, but not permanently, right? So there should be a constraint there. So C1 to 1 is equal to 0. That's our identifying assumption. Okay? So we can refer to our previous derivation and see what, in terms of fourth equation, what that means. Let me show you what that is. So this one, all those coefficients in this polynomial is assumed to be 0 when they are all add up. Okay? And if you check our previous step, this cell, this block being equal to 0 amounts to that equation. Okay? This one. And covariance matrix is this one. Okay? So we have this equation, the fourth equation, and three more equations that is related to these three numbers. There's a covariance matrix there, this one. And A22 of 1 is sum of these two coefficients. And this one. These are from VR estimation, right? VR estimation. And this is objective function. First equation, this is C110, C1 to 0, C210, C2 to 0. So when I receive 4 initial guesses, and these are my C0s, component of C0s. And left-hand side and right-hand side, the difference has to be something close to be 0, right? Similarly, these three are the differences. And we add that up and try to minimize this one. Right? So differences are minimized. So this is a rough way of doing it, but if you use, well, I set up this sum squared function in this way and try to minimize some of these differences by calling this optimum. You've seen this Gauss function previously, and should find 4 coefficients, these numbers, when it's done correctly. But in Gauss, we have some function like NLSys, nonlinear system of equation solver. That NLSys function, when it's called, then what you do is you do the same thing, calculate this, and return this as a vector. This one. Not sum of this one. Then you try to minimize this. So whether you use this naive minimization routine or using a more sophisticated system of nonlinear equation solver, you should get pretty much same result. So when I run this program, basically I have these 4 estimate as a C0, 2 by 2. Accidentally I calculated t-value on that, but it doesn't count because in this calculation relation is nonlinear, so t-value doesn't apply. So all you need is this number, and as you can see that the gradient is 0, so guaranteeing the minimum. And objective function is practically 0, right? So you solved exact solution for 4 equations, 4 unknown problem. Okay. So this is your estimate. This one, that one, this one, and that one. Right? It is easy to calculate inverse matrix of this. Right? You have already this one, right? Residual. So if you run a regression of this on lagged value, and constant, basically this is E1t, E2t, residual, right? I've shown this one previously. You run a VAR and choose view representation, and it will show you this expression, right? Then you can say series or generate your name E1 as dependent variable minus your representation. So get this, get that, and then, then we need to, basically this residual 1 and residual 2s are VAR innovations. So these are 2 series, right? 2 series has time index, right? C0 estimate is 2 by 2 matrix. And in EBUS, you can't multiply series with matrix. So you have to have same dimension. So what we do here is we group residual 1 and residual 2 from VAR to estimation as this name, residual vector. Okay, I give any name. I'm grouping it and give name this one. And here is the way we define matrix. 2 by 2 matrix C-mat. Okay? And how to assign a value to that? First, you declare C-mat as a matrix with 2 by 2 dimension. 1, 1, 1, 2, 2, 1, 2, 2 is accessed in this way. Right? And then we calculate this inverse CMAT as matrix inverse CMAT as CMAT transpose and then inverse to make this dimension correct. So what we do is we have dimension matrix here, and then here CMAT transpose and inverse. So when we write C0 ET was it that? ET equals to C0 times epsilon t, right? And in this case, what we are trying to calculate is residual matrix, and this one is 2 by 2 inverse. But you see, this one is 2 by 2, right? At particular t, it is correct. 2 by 2, 2 by 1 is 2 by 1, right? At particular t. But if we have cap t by 2, so 2 by 2 times cap t by 2 cannot be multiplied, right? You have to change the order, right? So what we did was this one so whatever we did in a previous presentation of the relationship, this is the way we calculate new residual, which is structural innovation, where you have a residual matrix multiplied by inverse of C0 matrix. Then this one is what you're interested in. Again here, probably you haven't seen this command, right? I just defined a residual matrix in this way, and this command is series to matrix. Series to matrix. So these two are the vectors, right? Vectors. I grouped this one previously, right? Vector E. This is vector E. 2-element vector. 2 matrix. A matrix is this one. And then I operate matrix manipulation here. This times inverse C0 is STR residual, but that's another matrix, right? So matrix times matrix is matrix, but this hasn't been declared, so I use this matrix declaration. And then I can change this one, this matrix, to series. Matrix to series. Then if I print this one, then I will see string STR residual series. STR residual series have two series. The first one is what we define as real shock. The second one is nominal shock. Okay. And this is a plot. And our sample period ends October, right? Real shock, nominal shock. And we know exchange rate toward the end of this sample increased, right? And what was the cause? The nominal shock appears to be going down, right? The real shock going up, right? So it appears that the shock affected, where is our series? Oh, okay. I didn't show you. Okay, first of all, this was Gauss code you've seen. So when I run OLS from EBUS, these are my covariance estimate, and these are appropriate A of 1. And running this program, you get very quick answer. These numbers, right? Numbers. Then this is M data, where you start with $1 exchange rate and US CPI seasonally adjusted. Korean CPI seasonally adjusted. So you start basically from two CPI figures and $1 as this walk file. Then rest of them are created by sample code. Okay? So let me bring if we take a look at this code, from current path, you read this monthly data, walk file 1, and the sample period is this. So log $1 and this and that. You calculate real $1, right? The log of nominal $1. So these are two variables. And then we can fit did it go? Let me first run this one first. Estimate where and difference Yeah, this is basically a result. Okay, I forgot. 100 times. 100 times. These are the same except interceptor, okay? Because I multiply that by 100. Here, view representation, and this is what I'm talking about. Okay. So what is residual 1? This minus everything on the right hand side, right? That's our residual 1. Oops, where did it go? Yeah. This part. Rest of them are the same. So if you look at real, where is the real? Real log This is basically data. Okay. So this is the real exchange rate, and there is nominal exchange rate. Okay. The difference is reflected by the price difference. Okay. What else do we have here? So first thing is we can actually identify shock. So if we keep going and figure out, we have this estimate, right? But we know that we can get everything here, right? And we know that appropriate numbers are actually the measure for impulse response, right? So we can do that kind of exercise. So we can say, what if there is a permanent shock now on the future path of real exchange rate and nominal exchange rate? And obviously, during this period, if we actually decompose series into these two parts instead of regular E of t from vector autoregression, we know that more importance is coming from this real shock. And when I actually fit gauge 1-1 process for this one, series SER01, this is what I get. So if you are calculating this type of thing in real time, probably you start observing, another hike in the real shock component. So this could be, quite a valuable exercise if you're actually interested in, anticipating this kind of as you go along here, the volatility is large, get large, right? Now we know that here on, Series 2. Let's take a look at Series 2. See? So this one, STR residual series, is the time series version of this matrix. Okay? In matrix form. And because I translated this one, matrix to series. Okay? So this is contemporary normal shock. So if you estimate arch let's not worry about coefficient estimate. Don't see much of the movement, right? Actually, this is not fitting that well. Let's try T. Or this one, Yigarch. It doesn't fit that well, but you don't see any movement from here, right? Up to the volatile period. Okay. And this part is not explained in my my book, but if you have your series, you might want to see whether what is the portion of variation explained by, let's say, permanent component compared to transitory component. So if permanent component is computed in this way, then those are temporary variations, right? And this is permanent move. Right? The way you do it is you have RT and ET, right? Real and this, right? So let's say this is XT. You want to calculate the variation of this one, explained mostly by agri-supply shock. That's your permanent component, right? So this is how you do it. Now construct new E of t of VAR. We have E of t from VAR already, right? But let's recalculate new E of t according to this configuration. C0 multiplied by, this is the one already computed, and constrain this part 0. So we zero out nominal shock part. Nominal shock. Okay? So this is your new ET. Then we have estimated VAR, right? we have initial condition for data, right? Initial value. We have initial value, right? Because we have estimated VAR, you can recursively calculate these two using not the original ET, instead this ET. This ET. Because this is in terms of log difference. If you keep adding, starting from initial value, if you calculate, if you keep adding this one, then you might find something similar to this one. So that's the way you calculate that. I haven't done this one, but I think that should give you the answers to the problem. Okay. My runny nose problem getting worse, but let me finish up this. Suppose you can handle this problem well up to this point. Then you might be able to apply this method to answer many interesting questions. For instance, here, Falk and Lee in 1998, they wanted to apply this method to find this line for farmland price, land price. Okay. Obviously, if this is the case, there's overvaluation, undervaluation, right? Temporarily. You can read it from this journal, American Journal of Agricultural Econ. Excuse me. Where they have three variables. 1, 2, 3. So covariance matrix, it will be 3 by 3. Right? The first one is the first difference of the log of real rent. So if I have to pay for, let's say, for the land to use for a month, I pay rent, right? That's rent. And real rent and its log difference. And the second one is the difference between this and real interest rate. The third one is P minus D, where this is real rent in natural log. This one is real farmland price in natural log. The original work method, when developed by Campbell and Schiller, this is sort of stock price in natural log, stock dividend in natural log. So this is real interest rate. And they try to translate their dividend ratio model in terms of three variable VAR process. And they wanted to calculate, well, if this is a real stock price, what is the fundamental value? And if this is the case, then, if these terms are like 10 years, well, 10 years of bullish market, about 10 years of bearish market, that sort of argument. Okay. But we've seen this one, except it has dimension 3 instead of 2, but structure is very similar. Vector is in this way, right? This is structural form. But you have now 3 errors here, right? Innovations. So they give some particular interpretation on these 3. The first one is fundamental or real shock. Second one is sort of quasi-real shock. Third one is nominal shock. Okay? Then because you have now 3 by 3 covariance matrices, but still you need identifying assumptions. So if you read this paper later, this is very similar to what we've seen. In our 2-variable case, we need one restriction, but you need to introduce 2 more restrictions. So when you're done, everything, the dark line is the real one, and this dotted line is what you call fundamental component of real price. So you can answer this kind of question, this math. So if you are asked to do something similar to this one using time series method, this is the one you probably want to go back. Of course, finding this fundamental value could be done in using other method. For instance, these 2 authors and myself with my students did from working paper last year. This is a real stock price, real housing price, US, and this is the fundamental value we calculated using their method. Okay. Their method ends right about here because of a sample. We extended that sample, but we still find very similar result, meaning our replication appears to be, as good. So what it says is, first quarter of this year, housing market is still slightly below this fundamental value. Right? Applying same method to Korea, starting from first quarter of 1997, this is basically what you see. So this one is second quarter of this year. So we are, I think, below fundamental value, which means in recession in Korean housing market. Actually, apartment in Gangnam area. Okay. But because of the lack of data around this period, we had to calculate fundamental price as a version 1 and version 2, but the movement is very similar. Right? I didn't show you, the detail of this method to produce this one, but you can always go back to, their reference. Lastly, well, this is a situation. Structural model in general has a shape like this one. Suppose you are building a macro model, big macro model, where you have many macro variables of interest. Okay. Then typical situation is variable 1 and 2 may be contemporaneously correlated at time t. So non-zero B1, 2 means this and this are related, right? So x1t equals to B1 to x2t on the right-hand side with negative sign, right? Along with some constants and lagged dependency like that. It could have more lags, right? So if this is the basically what you're interested in. Then, writing it in a compact notation, let's call this one as B and A0, A1. So this way, okay? And then covariance matrices. And you're assuming these are structural shocks. Structural shocks. So you can think of many different structural shocks. You can provide some good, interesting economic interpretation on the definition of these shocks. We previously seen that we have nominal shock, real shock, or permanent shock, temporary shock, or technological shock, or foreign shock. You can think of many different sort of shocks that might have interesting economic interpretation. But the problem is because you have a data X. This is basically what you can estimate, right? If you have a data X, this is basically what you can estimate from VAR using EBUS. Okay? Where you have interpretation here, zeta 0, which is the product of this one, and that. Okay. So you get this ET from usual VAR, but now you need to recover structural residuals as well as all those coefficients. So you can easily think that you need some restrictions to identify this kind of system. Right? And when you identify a system, then rest of the thing argument goes as before. If you can estimate this in somehow, then you can calculate epsilon t as b times E of t. So the question is how to identify those using VAR. And you can search for references where they develop large-scale macro model using this structured VAR approach. Okay. This is all I have to say for today. Sorry about my runny nose and voice. Questions? Okay, then on Thursday we will talk about GMM. Okay, I uploaded a Gauss program and EBUS code as well as EBUS work file, so you can replicate this result at your convenience. Okay. Thank you.